Hello, good afternoon, everyone. How are you guys doing? So before starting our lecture today, I just want to check with you any questions about assignment one. Assignment one is due tonight. So hopefully you guys have been working on it.
I have a small question about assignment one.
Yes, Peter, go ahead.
So for the second part, for the units for the sugar, I believe, like in the example, you show the sugar 0.75 tablespoons, but then the variable says sugar in cups. So
yeah, that's okay. Good, good catch. You can use tablespoon. Sorry about that. Yeah.
Okay.
Yeah. Let me think. I'm thinking about the recipe itself. Actually, should be cups because
Okay.
12 pieces usually use. I can't remember the.
Yep.
I think it's 1 cup or something like that.
Yeah. Tablespoon is too small.
Yeah, it's too small. Yeah, you want the muffins to be sweet, so definitely. But yeah, good catch. Good catch. Sorry about that.
Okay, thank you.
No problem. I will fix that in the description, but either way, if you guys implement it with tablespoon or cups, doesn't really matter. Okay, but it's a good observation. Thank you for noticing that. Any other questions? Okay. So if not, let me start by sharing my screen. So we're going to be having our lecture, and then we're going to also have another assignment posted today. It's already posted, but we can talk about it after the lecture is done. Okay. So let me see. You should be seeing my screen now with the slides that are also posted in the website. Let me see what's my chat so I can monitor your questions. Perfect. All right. What else? Okay. So what we're going to be talking about today is something called scripts and libraries. And it's a little bit of a continuation on these ideas of functions, but a little bit more general as well. So this is the plan for today. We will be talking about scripts and also libraries, which is even a more general concept. So the idea here is that, as you have done on assignment one, and we have been discussing in some of the lectures, we are going to be creating our own functions. Okay, and you will see one of the recurrent themes or topics in this class is that you should only have one version of your functions that you can reuse multiple times, but not having multiple copies of them. The idea here is that you will create a function, you will put in a file, and whenever you need, you will reuse that function coming from this file. Why? Well, there are many different reasons why you want to do this. One of the main reasons is that by just having one copy of your function, you can be certain that you are using always that particular version of the function. If you have multiple copies, and let's say that one day you figure out that one of these this function has a bug, has a problem, then you need to go and fix all the other versions that you have floating around of your function. But if you have only one version, then that's it. You fix the function, you test your function properly, and then you are certain that you are using that particular release, that particular version of your functions. So the idea is that we will keep our functions in files, and you can keep more than one function in a file, so related functions can be part of the same file. We will like to have functions with proper names and file names that are representative of what the functions do. So that will be part of the best practices. We're going to be talking about this probably, I don't remember, next class or class after, but we're going to basically summarize all these concepts and all the best practices that we should follow for having well-organized code and well-organized functions. Now, the idea behind this is called modularity. And I think I mentioned this a couple of times. We have functions, we will have scripts that contain functions definitions. We can even have a script that contains data definitions, and all of this will be part of one unit, one module that we can reuse multiple times. So we are going to learn how to do this in R in particular today. So this is an example. What I have here on the left is a file. It's called myutilities.r file. And what it has is two functions definitions. One that is called double and subtract 3, and that's exactly what the function does. It computes for a given number, it computes the multiplication by 2, and then it subtracts 3. And then the other function is min or 0, which basically computes the minimum or 0. So if it is a negative number, it returns 0. If it is a positive number, it returns the minimum of, and in this case, it can be a vector, right? So the function has one argument, as in the other function. It computes the minimum, and then it as is the minimum of the vector. In this case, is smaller than 0. It assigns m to 0 and returns m. Okay. Now, these two functions, as you can see, as you did in the assignment probably, are written in a file, and my file is called, in this case, myutilities.r. What it means is if I open my R session and I just type double and subtract 3 and then the number 10, then R will complain. I could not find such a function, right? Because it's not defined. It's written in my file, but not defined in the R session. So how can I load? This is one of the first things that we're going to learn, although you already did this for the assignment, is how can we load the functions definitions that we have here? Well, by using the source command. So source and the name of the file basically reads the file. It's like if you were typing in the terminal in R, exactly this command. So in this case, I'm loading the definition of the double and subtract 3 function and the min or 0 function. And so after sourcing the file, now I can use double and subtract 3 of the number I want, min or 0 of 10, then I get 10, min or 0 of minus 10, I get 0. And this will work also for vectors. So if you have a vector, then it will also work. So the source command is the way that we have to load functions that we have previously defined in our files. Okay, again, I think you guys already did this in your assignments, so you're probably familiar with this. Now, one of the things, and I also mentioned this, or at least I try to guide you during the assignment, is one important thing to source your files, to load your functions definitions, is to know where the file is located. And for that, we have a couple of useful commands. I think we mentioned this very quickly. Get working directory. It prints in which directory, in which folder in your computer R is looking for files. So for instance, the default one is what we call our home directory. In my case, I'm using one signed computer, so it's C user signed. But I can change that directory using the set working directory. Let's say I have my functions in a temp folder. So I can set working directory to temp. These are strings, by the way. And then if I do get working directory again, then I get the subdirectory temp where I'm positioning. Jim is asking, is there a way to permanently set a working directory, or do you set it every time you open the R console? Excellent question, Jim. Yes, there is a way. You can depending on what interface you are using with R, if you are using the console or if you are using, for instance, R Studio has a pull-down menu that allows you to do that. In R, I believe I can look for that and post something in the forum if you're interested. I believe you need to modify an initialization file that looks for. So every time you open R, it will look for this file, and it will tell R, okay, go and set the working directory to this thing. Now, one thing I want to warn you, I think I mentioned to some of you during the office hours, is do not set your working directories in the submission file, in the files that you are submitting for the assignment, because those will only work for you. You are free to assume, you're welcome to assume that I'm going to put your files in the same directory, so your script and your functions definition in the same directory, so just source and the name of the file should work, okay? That's an important point. But Jim, if you're interested, let me know or post something in the forum. I can post the recipe there. The reason I don't have it here is because it depends on which interface in particular you are using. If you are using just the R console, or if you are using R Studio or the R GUI interface. Okay, but yes, there is a way to set the working directory. One thing that is useful as well as set working directory and working directory is the dir command. The dir command lists the current files that are in the folder that we are positioning, meaning which are the files that R has access to in that current directory. And then ls basically tells you which functions have been, or which variables as well, have been loaded when you source the file. So for instance, in the previous example, I had double and subtract 3 and min or 0. And if I source the file and then do ls, then it lists the name of these two functions defined in the file itself. Okay? Any questions about this? Okay. So I know one thing that you may notice, and this is something that is more as oh, Vishendra is asking why ls is giving. Oh, that is because you probably don't have any functions defined at all. So one thing that ls don't show is in my notes here. It doesn't show predefined variables like the number pi or the number e or anything like that. So if ls is giving you character 0, means there is no function definition, no user defined function or user defined variable in this current setup, in this current session of R. Okay, makes sense? Good question. No problem. So one thing that may happen to you is, okay, let's say that we are working in one of these assignments, I'm defining a function, but then I realized that I had a typo, right? So let's take this function, for example, I'm defining a square function that takes an argument and then returns the square of that number. But as you can see, I had a typo here. So I source my square code.r function. But then I try it and I obviously realize, okay, this is not 16, 4 to the power of 2 should be 16, but I'm getting 8 instead. That's because I forgot a star. So I change my code, I update my code and I save it. So the way to update your function definition is to resource your function again. So when you resource, again, this is like if you were typing in the console live, R will reread your file and now take the updated definition of your function, and then you try it again and it works. Okay, so this is more of a pragmatical thing than anything else, but it's important to be aware about this. Okay. Now, one thing that is related to a script is there are many functions, and we're going to see some of them during this course, that are already predefined for us, not being part of the standard R ecosystem, but also that can be loaded by installing additional libraries. For instance, this is just an example of a data set that has some chiroptera data. And this chiroptera data is not part of the R built-in data sets. It's part of a library called APE, which stands for, what was that? Some sort of epigenetic data or something like that. I don't remember exactly, but it's a package that you can install in R. Now, for accessing that data, what I have to do is library ape, and then I can use that data. Now, you may happen to don't have this library, and what we're going to see today is how to install these libraries as well. Okay, so this is all just to let you know that there are additional functionalities that you can include in R by installing packages that are not part of the core system of R, but they are, as we mentioned, I think it was in the first class, there are two main repositories that are curated and are peer reviewed by the R community, which is the CRAN repository and Bioconductor. We are going to be focusing mostly in CRAN packages. But if you have a question about Bioconductor, feel free to ask. Many packages you may find in one or the other, but these are the to-go places when you want to install additional packages that are not part of the built-in functions in R. This is another example. Again, you may happen to try the library ape and not be working. So the way to fix it is, as with the library fun here, this is a library for recursive call to functions. It's used in machine learning sometimes, is to use the install.packages function in R. So you will do install packages, and then this must be between quotation marks because it's the name of the package. And then you do fun, for instance, if you want to install this package, or you do ape, as in the previous cases, you don't have ape installed. Ape is one of the cases that don't come with R, so you will need to install that. But any package that you will need, and is part of the CRAN repository, you will do install.packages and then quotation marks and the name of the package. Okay, so that's how we install packages that are not part of the R built-in functions, right? After the package is installed, then we're going to do library. And then in this case, it can be the name between quotation marks, it can be single or double quotation marks, or it can be just the name, okay? So you can just do library fun or library ape, and R will recognize that and load all the functions defined in that package. So in some way, the library command works pretty much the same as the source command for our own functions. But now you're loading functions that have been created by someone else. And it can be functions or it can be data sets, different kind of things, all right? So source is for loading our own functions definitions in a particular file. Libraries for loading function definitions or data sets that someone else has created for us. But be aware that before using the library command, or if you run the library command and you get error in library, there is no package called X, you probably need to use the install package command to install that package. Okay, so we have seen 3 or 2 commands so far that we haven't seen before. All right. Okay. Now, one crucial part, any questions about this? Okay. One crucial part of coding, I think we talk a little bit about this, and again, this will come back when we do this kind of conversions class or lecture on coding best practices, is including comments in the code. And if you go back and see some of my examples here, I have a few comments there, the name of the function, what these functions achieve, but also within the function, what are we doing? Like this if statement, what it's doing is getting the minimum or 0 depending on the value of m, right? So we usually, not usually, we always should put comments in our scripts and in our functions explaining what the functions are trying to do. And what kind of things are comments? Well, what are you doing? Why are you doing it? Why this function can be useful? The assumptions that you are making, sometimes we are assuming things, and these kind of assumptions should be stated in the comments. And what are the plans, the future plans for the code? Is this going to be part of a release? Is going to be a stable version? All these kind of things. Any programming language has a way to comment code, and some people say there should be as much code as lines of proper code, so 50-50. That may be is too excessive in some cases, but commenting code, especially the parts of the code that are not so clear, that are a little bit more obscure, is really important, okay? Some people like to drop a knock show. I personally don't do it, but I know people that do it, and you have a good style, why not? Starting, I think I mentioned this in the description. Some of you, especially that you show me your code during the office hours, I mentioned to include some comments. It's not going to be mandatory for this assignment, but I'm going to comment on not having comments on the code. But starting on assignment 2, you will be penalized if you don't have enough and proper comments, okay? Just to, I think we mentioned this, the comments in R starts with the hashtag or the number sign. So again, we're going to even deep a little bit more about different type of comments and documentation in a second, okay? But comments is really, really important. It's really crucial part in coding. Documenting your functions, and this is a related concept, but not exactly the same as commenting your functions. It's done through comments, but it's not the same thing. So what is documenting and what is comments? So comments are things that explain what the function is doing at the level of the code. Documenting explains to the user how to use this function. So let's go back to my example of the min or 0, right? And what this function is, it computes the minimum or returns 0 from a vector, right? That's the comment the user who is going to use this function wants to know, what the function does, what arguments the function should receive, and what is going to return the function. Those are the main 3 things the user needs to know from a function: what the function does, what expecting to receive the function to perform what it has to do, and what the function will return. As a user, I want to know that, right? It's a black box for me, but I need to know what I need to fit into the function, what the function will return to me, and what the function is expected to do. Those are the main things, and that is what we call documenting the function. Now, how it does it for the end user, it doesn't really matter, but for the person looking into the code, it does matter. So how it computes the minimum or the zero is a comment that I will put in how the function works, but not for the end user. So this is an internal comment for the coder, for the programmer looking into the code of the function. Okay, so that's the main difference between commenting and documenting codes. So how we different, is that a difference clear, more or less? I always get this question, okay, what's the difference between comments and documentation? And I would say, well, the documentation is for a third-party user that doesn't necessarily need to look into the code of the function, what things the user needs to know. Inputs to the function, outputs of the function, and what is the functionality of the function. That's the documentation. The comments are, okay, for the person looking into the code of the function, what it needs to know how the function works, okay? So for documenting functions, R unfortunately doesn't have any built-in functionality. So for that, we're going to use an additional package called ehelp. And what the ehelp function is, after you define a function, you can decorate the function with this hashtag and quotation marks, single quotation marks symbols. And these comments now are special comments related to the functionality of the function. So for instance, let's take my utility files, and I'm going to start to populate the definition of the double and subtract 3 function. Originally, it just has the title, but now I'm including all these other comments. So I'm saying, well, the function definition remains as it is. Nothing has changed there. But now I'm putting hashtag or number symbol, single question mark, the name of the function, and then describing what the function does. This function doubles the argument, subtract 3, and returns the result. And what I'm defining is with this add param is a keyword for the ehelp package, is defining that the argument that the function is expected to receive is a type numeric, is a number. Okay, so again, this is going to be again part of the of coding, of best practices coding. Now, bear in mind that, as I mentioned before, the ehelp package is not part of the build R function, so you need to install it with the install package function. I'll show you in a second how to do that. And if you want to see how more keywords and documentation, you can visit this website. Okay. Now, how it will look like is, this is again my function definition. Nothing has changed. It's the same repetition of the code so that we keep it present there. I'm going to source the utility files that describe this, because I'm assuming that you guys don't have the ehelp package. Ehelp stands for enhanced help. Many other languages like Python, for instance, had this way of decorating comments so that it works as documentation of the functions. It goes by the name of docstrings. And this package is inspiring that to create the documentation. The way it works is you will need to install the package, and this one you do only once. You don't need to do it every time. You don't need to put in your scripts. You can assume that the user has this if you wish, and you do this once. And then you load the ehelp package, so this one, and then you ask for, okay, help on the double and subtract 3 function. And what the ehelp package is going to generate a help page very similar to the help page that you will get with help and the functions defined for R. So now the ehelp package will say, okay, this is the double and subtract 3 function. It gives you the description of how to the description of what the function does. It gives you the description of the arguments. It tells you how many arguments and which arguments and what are the type of arguments based on the param keyword. But it also can tell you how to use the function. So it looks at the function definition, it looks at the argument, and that's it. You can also add examples. So there is a add example keyword that you can do. And you can also do coloring, so it has some fancy stuff that you can also try. So it's something for you to experiment a little bit. But again, the bottom line of this slide is that this hashtag single quotation mark represents documentation for the function. And in the same token as comments, we are going to expect to have this describing what the functions try to achieve, describing what the argument represents or is expected to receive, and what the function is supposed to return. You can go further on this and decorate with examples and test cases if you want, but at least this is the minimum that you should put in your functions, okay? And as I said, there are a few examples in the Git repository of this package. Okay, any questions about this? All right. Now, we have seen a little bit of how to create functions. You guys have done this already in assignment 1 and save it on files that we're now going to call scripts. So one way to think about a script is just a list of commands that you want the R interpreter to execute, to run for you. And in the same way I can create functions, I can just put, for instance, lines of code that will be in R. So for instance, I'm creating a matrix here, I'm creating a vector, and I'm using a function from R to solve a linear system of equations, and I'm printing the result. It doesn't really matter what it does, it's just a sequence of commands that you will keep. What is the advantage of this is if I say my commands, of course, I can try it first on the terminal and be sure that they work and they perform as I would expect to perform. If I do it this way, then I can reuse these commands as many times as I want. So there is no need for me for every time I want to, try this to be typing this all over again. But of course, these commands, if written in this particular manner, will only execute these particular commands, this particular case. So one way to do this is you say this is in a script, my script.r, for instance, and then you execute this by, again, sourcing the script, and that will go and load each of the commands and write it. You may notice the difference in my slides when I do this greater than symbol. It means that now we're working in the interactive interface in R, when I write in this way, where this is just saving a script or creating the content in a text file, just to clarify that, okay? Now, there is another way, and we are not going to use this extensively in the course because it will require for us to spend 1 or 2 more lectures in a different theme, in a different topic called the shell. But I just want to let you know, because it's a very, very important part of R, and it's how many people use it when you're running in supercomputer centers or in clusters or in computers with a Linux environment. So the most powerful thing of R is when you're running what is called batch mode. And what does it mean? It means that instead of you being typing commands interactively with R, you can save all your commands in a script, as we saw before, and then ask R to execute this script independently of you being in front of the computer or not. So how you will do that? Well, source is one way to do that. If you have your R terminal open and you type source and the name of your script, R will go and read the whole script and execute line by line. So that's batch mode. That is processing things in batch, meaning you read the lines that you were executing or you would like to execute, and R will go one by one and execute. You may wonder, why is that useful, sort of? I could just be looking at the commands and see. Well, it turns out that when you're doing really heavy data analysis or really heavy data processing or computations even, it may take a really long time. So for instance, my programs, of course, they are not written in R, they are written in a different language. It can take months to run. But I know people that runs data analysis pipelines in R, and it takes at least from several hours to several days, depending on the amount of data they had to process, right? So R also offers a way to run this without the interface, without the R terminal. And the way to do it is, usually this happens on a Linux environment, in a Linux command line, in a terminal. And what you write is R command batch. That represents that R will run in batch mode, in this mode that is unsupervised without the user in front of the terminal, and then the name of your script. When you run it that way, if your script is called myscript.r, R will produce a myscript.rout for output, showing all the results that you will obtain that will be displayed on the terminal as if you were looking at the terminal, but is saved in a text file. Another way to do this is using R script, myscript. So these are 2 equivalent ways to run this. And again, if we were looking at this example that we had before, the running R command batch myscript.r will basically generate myscript.r out Or if you run R script myscript.r instead of R command batch, what it will do is it will print on the screen what you were supposed to get. Okay. Now, one word of warning is you're supposed to have the R script or R in your path. That is the environment where the operating system goes and looks for the executables. I don't want to go really too much in detail here, but it's just more than a word of awareness here to let you know that it's possible to do this if you are interested, because you think that you may be in the case that you need to do very heavy data analysis or data processing. You let me know and we can chat in person about this. But as I say, usually when I teach this course in a long format or longer format than the one we're doing here, we spend 1 or 2 more lectures talking about the shell and how the shell interacts with R. But we're not going to be, it's not going to be part of our course, but I did want to let you know because I feel this is a really powerful thing that you can do when you are programming in R, okay? All right. I think there is one more thing. So this is a little bit of convention and some things that you probably guys are already doing. By convention, all the scripts, all the text files that define functions in R or defines commands in R end with the .r file extension. So that's easy for R to know that it's an R file or an R script file, and for the users also to know, okay, this is a program written in R, okay? We mentioned put comments every time. Even if you doubt about it, just put a comment. Just if you want to have a start, you can start by saying what the name of the file is, what functions are defined in the file, who is the creator, when did you create it, those kind of data fields that we usually put to identify the work we are doing, just put them. Document your functions with the doc strings that we saw before, hashtag single quotation mark. The main things we want to know in the documentation is what the function does, what arguments the function receives, what the function is supposed to return. And if you are keen enough, you can put some examples and things like that. When you are saving files, when you are creating these scripts, and you probably went through this, do not use a word editor like Microsoft Word or LibreOffice or anything of those. Use a text editor. And actually, if you use a good one, a code editor, as we call, it can be add-on, it can be Sublime, Brackets, Emacs, BI, Nano. They will color code your code, and that makes things easy for you to see. What else? We talk about the source command. I mentioned this. Some IDEs are also useful, like RStudio if you want to use, or even the R GUI. Okay. Any questions so far? I think we had at least formalized some of the concepts that were floating around, some of the assignments, or the assignment, we have only one so far. But now we are going to formalize even a little bit further, okay? So we talk about scripts, we talk about functions definitions that go into these .r files. What we are going to make the difference now is between what we call utility files and main driver script. So what are utility files? Utility files are files where you basically define auxiliary functions, functions that you are going to use for running a particular program. And then your driver script, or your main driver script, as some people call, is the file that actually source your utility files, create some variables, and execute your functions, and basically end up doing whatever it has to be done. Okay? So let's take again the example of my utility files, where I just define the double and subtract 3 function. This function is quite simple. It just basically receives a number or a vector, it multiplies the number or vector by 2, and then subtract 3 to the number or the vector. So how will my driver script, my main driver script, look like? Well, the first thing is it will identify itself with a comment saying, okay, I'm a driver script and I do whatever I have to do. Then it's going to obtain the functions that it needs to use in the driver script. So it's going to source the utility files, and then it's going to perform some analysis. So for instance, in this case, we are generating a vector from 1 to 20, and then we are calling the double and subtract 3 function with this vector that we just generated, storing the result in a variable, and then saying the answer is whatever that was the answer of that computation. Okay. So main difference between utility files and driver script is the utility files define these functions that can be used by another script or another program, but are not basically restricted to that program itself. It can be used for other programs. And this is a simple function. It's not too profound. It's not too convolute. But I could reuse this function in another script. I can have another driver script that does something different, but still wants to use this function. And the only thing we'll do is source the utility files and call this function with another data set. Okay, is this clear more or less the difference between the driver script and the utility files? The other thing to bear in mind is when we want to execute the commands, the lines of commands, the program we want to run, you're going to be sourcing the driver script. And the driver script will cascade down to source the utility files that need to be sourced. And of course, it could be more than one utility file that the driver script may need to use. Okay, we may see examples of this in the assignments, in the future assignments. All right. A couple of commands that are useful sometimes to include in your scripts or in your utility files are the save and load commands. So save is used to save variables that are part of your environment. For instance, if I define a variable A to be 10 and a variable B to be 20, I can decide to save these variables A and B and then specify where to save it. So my variables A and B are going to be saved in a file called mydata.rdata. And this is a specific data format from R. It's a binary format, so you won't be able to see in any other way. You won't be able to double click in this file and open an interface or anything. The only way to recover this data is to use the load command in R. So if I load mydata.rdata, it will load the variables that we saved, A and B, and it actually will call them in that precise way as we call it before, A and B. So this is a way to preserve data if you really want to, okay? We're going to be talking more about this, but I just wanted to let you know we will have a whole lecture on file I/O, file input-output operations, how to save and recover data, which is a good way and a bad way to do that. But this is a quick way if you really need to save data. One way I will not recommend to do is when you are exiting R, R will ask you, do you want to save your session? And basically what R does is you say yes, it will look at all the data, all the functions that you have defined in that session and save it in a file that will automatically load whenever you open R. This may sound useful and a quick workaround, but it's basically you don't have control on that. After you say yes, you basically dump all the garbage that you have there, and maybe you were just testing things and you may not want to carry all that baggage. So one way to basically eliminate that is to remove a file that are preserved. So if you run into this issue, just let me know. I'll tell you which is the name of the file. I think it's called .rdata. It's a hidden file, but it's easy to spot if you know where to look, okay? But again, something to be aware of. Some people don't mind. I personally don't like because it's a lot of baggage, extra baggage that you need to carry when you are testing things that don't make sense just. Okay. So as I say, another way to invoke this process of saving the actual session, if you really want to keep all the functions, definitions, and data that you have there, is to use save.image. So basically, save.image does exactly what the question when you are exiting R does, is asking you, do you want to save all the information in the current session? So save.image does that. Alternatively, if you want to be a little bit more careful, you can do save.image and then specify in which file name. So if you really want to preserve your environment, you can say, okay, save.image file, and then this is my working test environment X, right? And .rdata for convention again. And then for loading that environment, you do load and then the name that you gave to the file. Okay, so these are some quick tricks that you can use to preserve the environments you are testing things or playing with data. Right. So quick summary, and I have some additional things to show you, and then we can discuss the assignment for the next assignment that it will be due in 2 weeks as well. So we talk a little bit about modularity, and now the actors are start to take a particular form and shape. We will have a utilities, and this is something that will start to appear in our assignments as well. We will have utility files and a main driver script. The utility files is where we define the functions. You kind of did already that for your blueberry muffins and your quadratic equation functions. without knowing it, but this is kind of what we were after. We will have main driver scripts where we basically source the functions or script that we want to use. There is the install packages function to install packages of libraries that are not part of the core R ecosystem, but you can do it from CRAN, for instance. Libraries to load those packages so that we can use the function defining the packages. And then if you are running from a terminal, good things to have in mind is R script or R command batch. Okay, those are two things that are quite useful to remember. Any questions about this so far? Okay, right. If you don't have any questions, I have some extra material in the next slide that I just want to mention to you. It's about what we call command line arguments, and this is when we are running again from a terminal. So this is what happens. So I have an example here of a second script. It's called myscript2.r. And now it has this additional line, which uses the function command args. And then it has a parameter saying trailing only equal true. What this function will allow me is to pass information into the R script and access it and do something with that information. For instance, what I'm doing here is after I receive this, I put this in a variable called args. This variable is going to be a list, a vector of strings, if you wish. And it's going to say, then it's going to print information about that variable. It's going to say the type of argument is, and then the type of, remember that function type of, it will say how many arguments are expected or were received by the script, length of the variable, and then it will print the arguments. The command line arguments are, and it's printing that variable, okay? So for instance, if I run with R script, I run R script, my script, 2.r, and then I write two extra things. And this is what we usually refer as command line arguments. And these are arguments. So in this case, I had two things, pans and 3.2. These are arguments that are passed to my script that is run through the R script. Okay, so in this case, it says the type of argument is character because these are strings, as I told you. The number of arguments are 2, or is 2 because it has pants, which is a word, and then the number 3.2. And then they say the command line arguments are pants, is repeating basically what I wrote, and 3.2. Now, the interesting thing is not just repeating whatever I wrote after the script, but this I can now access that information and do something with it. Okay? So this is a quite powerful technique because what this is allowing us is to take modularity up to a higher level. I have, if you remember, I have my functions which receive arguments, and the arguments are a way to communicate information into the functions, and the function then can do something with that information. Now I have scripts that I can source from R and execute then, like if I were typing, but now I have one extra degree in these layers of modules or functionalities. I have one extra degree that is I can run from the terminal, calling my script and passing information into the script. So in that way, it will allow me to communicate information even from the outside world of R. And in that way, if I'm running a very, very tedious data analysis process that I need to communicate, for instance, the name of the file where I want to run my analysis, now I could do it by using this technique, okay? Again, it's something I want to show you because I think it's one of the most powerful things that not only R, but many other programming languages like Python or C use. We are not going to dive too much into this because it requires that we have an environment that we haven't spent enough time creating. But if you're going to run in a cluster type of environment or even a Linux workstation, you will already have ready for you. So you only just need to know how to do it, okay? One more thing about arguments that is important to know is that arguments are considered strings, are words, are some sort of characters, text, okay? So if I modify my script, again, this is my script 3.r, then again, I'm reading my command line arguments here, the information that comes after the name of the script when I'm running in the console, and say, okay, if args equal to pants, then says pants have been detected. If args bracket 1 equal to pants have been detected. These two things do the same thing, but one is correct and the other is incorrect. The first one is incorrect because, as I told you, the R's is going to be a list. You saw this when we were running this, and it says number of args is 2 because we were computing how many elements are in args. And the reason why it's a list is because a priori, I don't know how many arguments the user can write. It can write, okay, pans 3.2 and then 24. And in that case, there will be 3 elements. And the way that R process that is to put these as elements in the variable R. The only way to do this is to do a list or a vector. And it uses a list because these are basically strings, okay? Now, if I run this, I get R my script 3.R and then A, and because A is not equal to pans, it doesn't write anything. If I write A and B, meaning 2 arguments, now the first thing will fail because it says if R is equal pans, the condition has length greater than 1, and this is because R in this time when it was created has 2 elements. So it doesn't know actually which one you want to compare. That's why the correct way to do this is to be explicit. Do I want my first argument to be pans or my second argument? Okay. But the way to access the arguments is by using the bracket notation, specifying that you want the first, second, or whatever argument. Okay. So that's an important thing to bear in mind whenever we're using command line arguments. The arguments come in a list or a vector because of all the same type, but it's the same idea. Okay. One final thing, again, is a subtlety if you wish, is command line arguments are considered strings. Even if you write numbers, they are considered strings. So again, this is an example where I'm going to read a command line argument and I'm going to ask, is the first argument equal to 1? Then I will say the first argument is 1. Is the first argument equal to quotation marks 1, meaning 1 as a string? The first argument is 1. It turns out that these two things work. It doesn't give you an error message if you write 1. The issue is that R underneath is doing what is called casting. It's converting, because what it has in R is always a string, is converting this value 1 as a string. So in principle, this is functionally speaking is not going to break your code, but theoretically speaking or conceptually speaking is not correct. So that's why we always should compare against strings and not just plain numbers, okay? Even if we're expecting a number. Another way to do this is to use as numeric and then force the argument to be converted to a number. This is tricky because if what the user actually input wasn't a number, it's a word, then the conversion may happen or not, and the code may break or not. Okay, so it's always if you are expecting something to compare to a number. Now, one thing that you can do, I think we talk about these functions, functions is something. We can say is numeric of something, and then it will say, or we can attend the conversion to numeric and check if we actually get a real number or not. Okay, so we can combine with some of the previous like NOS functions that we saw before. Okay, any questions about this? As I say, we are not going to dive too much into this, but I still think it's a good idea to be aware of this, especially if you have the chance or if you are planning to use this for your own research in an environment that allows you to do that. We are not going to do it in the course because it will take away from us a couple of lectures that we may need to spend or we may want to spend in something else. Now, I told you before, we have freedom to do some things in the course to adjust the themes or the topics. So if you think this is something that you could benefit from, we can spend some time talking about the command line. I haven't thought about that. Usually I try to cover topics more related to R, but if there is a clear interest in you guys about, you know, discussing this or seeing this more in action in the terminal, we can try to do that. Okay. Anyhow, any questions about this? All right. So if there are no questions, let's talk about assignment 2. See if you guys can see. Let's stop my slides here for a second. Just looking for, let me see where my browser went. Just opening a second one because I can't find it. All right. share my screen again so we can talk a little bit about assignment 2. So assignment 2 has a couple of elements in place. So we are going to be doing slicing and vectorization as we talked last class, but we're also going to be creating functions, okay, and testing our new functions. Just one second. Whenever I share something new, it takes away my chat window. So let me see if you guys can see this. Big enough. So the assignment 2 will have a few different parts. Okay, we are going to start by creating a file called myfuncs_assign2.r, which will contain the definition of 3 functions. Okay, the first function is going to be called harmonic mean, and it will receive one argument, x, if you wish, and it will compute the definition of the harmonic mean. Okay, the definition of the harmonic mean is 1 over, and then 1 over the sum of the elements of the vector x divided by k, being k the number, how many elements you have. Okay, so instead of the usual norm where you just add the numbers and then divide by the total number of numbers that you have, this definition of the harmonic mean takes the 1 over the number, add them all together, and then divide over the total number of numbers that you had, and then takes the inverse of that. Okay, it's quite simple to use, but one thing that you may want to be aware of is that if one of these numbers is 0, the denominator will blow up, because 1 over 0 gives you an infinity, and we don't know how to deal with those cases. So your function, what it has to do is it has to exclude any possible zeros in the numbers. Okay, and that's, as we probably remember from previous lecture, is what we call slicing. So we can basically remove those numbers by slicing the original vector of numbers that we have by the condition we want to exclude. Then the other functions I will suggest to use are sum and length, and of course you can use the help function as we discussed before to understand how they work. But basically, I want you in part 1a to implement the harmonic mean using slicing and vectorization. So I really don't want you to use for loops or conditionals whatsoever. So think about how you will implement this only using slicing and vectorization, which will be the optimal and more straightforward to implement this in terms of code. Okay, so it's clear what we have to do for function 1a. Any questions about function 1a? Okay, we'll take that as a no questions. For function 1b, there's another mean that we're going to create. In this case, is what we call post mean for the positive mean, and it's the usual definition of the mean. But now the condition is this function will receive 2 arguments. Okay, be careful with this. One is the vector of the numbers that we want to process. So this is going to be the usual definition of the sum of the numbers divided by the total number of numbers. But the condition is that we want positive numbers only. There is a second argument to this function. The second argument is called strict pos, for considering only strictly positive numbers. The default behavior for this argument, meaning that if the user doesn't specify this argument, is to exclude null elements in the calculation. If this argument is specified to be false, it's a Boolean argument, meaning to do not consider strict positive numbers, it will also include zeros. And in this case, there is no problem with this implementation because you are just adding, you are not dividing. Now, one thing that you should be careful, both cases, is to divide by the proper number of elements in the vector, meaning if I give you 10 numbers, but 5 of them were negative, for the second case, for instance, I will be dividing over 5 and not over 10. Okay, because the first 10 elements, the first 5 elements of the negative elements were not included in the mean. All right, so be aware of that. Okay, so this function has its usual function that you use to compute the mean, but only considering positive numbers, either strict or including the null element 0. All right, so that's our second function. Again, no for loops, no conditionals of any kinds here, only slicing and vectorization. And sum or mean are functions that are you can use and are considered vectorized functions, right? So, and I mentioned this, and I give you some examples so that you can test your implementations of what you're supposed to get. And these are examples for the harmonic mean and the positive mean, okay, with different vectors that you can create. Okay, so nothing too profound. Now, for part 1C, what I want you to do is to implement the positive mean function, but now using explicitly conditionals and loopings. Okay, you will, let me be clear about this. You will probably never want to do this for different reasons. One of the reasons is more work in the sense of coding, but also it's slower. So performance-wise, it's bad. But just to force you realize how complicated it can be, I just want you to go through the exercise of taking one of the functions. I pick positive mean because I think it's easier than the harmonic mean to implement this way. But if you prefer to do harmonic mean, that's okay with me too. Okay. The idea is that you will have to loop and you will have to throw an if statement within your loop. Okay. And one thing that you may want to be aware of is that you will need to use a technique like this. You will need to use what we call a cumulative variable so that you can accumulate the intermediate result. So for instance, if you were like, let's say here I'm counting how many elements are in a vector, right? This can be very easily done with length. But imagine that I don't want to use length because I want to go the hard way. So I will include a counter variable, initialized at 0 at the beginning, loop over all the elements in the vector x, and then add one. In this case, I'm adding the actual number of the values, so I'm using the equivalent of the sum, and then printing whatever is, actually this should say counter and not x, okay? So, but that's a way to loop over and use what we call a cumulative variable. Now, if you were doing this for the mean, what you will do is at the end, divide counter by the total number of elements in the array, for instance, okay? But again, this is kind of forcing you to implement one of the functions using for loops, just to be concrete. You could use a while loop if you want, but a for loop probably is straightest in this case, and conditionals. Okay, so no using vectorization nor slicing in this case. Okay, so 3 functions for this first part. Any questions about this so far? Why should the counter start from? In this case, it's a good question, Tapas. In this case, if I'm accumulating things, it will start at 0. And I will imagine in your case, it will start at 0 because it's like saying, what happened here, let me go back to this. It's an important point, or relatively important point, because it's a technique that appears in different styles or different techniques. What you're starting is a variable where you are going to add things, right? So what happened here is my first iteration is put counter to 0. So there's nothing in terms of numbers, there's nothing there. Now in my for loop, the first time that I go here, it says assign to counter plus something. We saw this example in one of the very first slides that we saw. I don't remember, first or second class probably. And what happened is whatever is on the variable counter is first evaluated on the right-hand side of the assignation sign, add to whatever was in x of I, so the element of the vector, and this sum is then placed in counter. In the second iteration, counter has been updated with this value. So now counter has, let's say the vector has 1, 2, 3, and 4. So it starts with 0. There's a 0 here plus 1. Then counter is updated with 1. In my second iteration of the for loop, now counter has the value of 1. X of 2 is 2. So it's 1 plus 2 now is 3. And counter is 3, and so on and so on. Okay, so if you are accumulating things for counting, either counting a number of elements or counting adding the value of the elements in the vector, I would say start at 0. And you need to initialize. This is what we call initialize the variable, because you are reusing this variable in this expression. If you don't do that, R will complain, the code will crash because it doesn't know what counter is, and counter has to be part of this expression on the right-hand side. I know the first time that you see this, it can be a little bit confusing, but that is also why I want you to experiment with this just to get used and think about what is actually going on in this expression. Okay, think about this, play with it before implementing it, and do let me know if you have questions. We can dive a little bit more on this particular piece of code. Okay. Good question. So yes and no. So the variable x is the vector. So if this was part, I throw this what we call a snippet of code, a tiny piece of code that you may want to use in your function. So your function will receive an argument, in this case, 2 arguments, but let's start with one, the vector x. So I will say x, I'm going to assume is given. Okay, it's part of the problem of the function. So the function will have a vector x that is defined. The I variable you don't need to define because it's defined in the for loop, right? When we do I in sequence along x, what happens is every time this for loop is hit, this iteration is, makes sense? So maybe let me see if I can. I'm trying to. Let me see if I can open a terminal. We can do a quick example here because I think it's I think it's an important point. I'm going to put. Here we go. I hope you guys can still see my terminal. Are you? Okay. So I'm going to launch R, okay, and I'm going to create a vector x. Oops. And I'm going to just put some random values, okay, 2, 5, 6, and 7. Okay, so that's my vector x. Now remember what sequence alone does. What instead of returning the actual elements in the vector, it returns the indices, basically the positions in the vector itself. So what I was suggesting to do is for I in sequence along of x, and then I'm going to just print the actual value of I, and that's basically it. So let me do this in a nicer way. Just put in a new line. So basically, it's printing the indices there. Now, if I instead of wanting the indices, I do want the actual value of x, I can do x bracket I, and that is what is written in the for loop I have. So now it's printing what is the index, but also the value of the element. Now, one thing I can do is say, okay, let's put cum sum, and I'm going to use cum sum as cumulative sum of these numbers, put cum sum as 0, okay? So I'm going to use my for loop again, and now in addition to that, I will say put cum sum as whatever is in cum sum plus, and here I'm going to take the value of the element in that particular thing. So in that case, I'm still printing the numbers, but then when I ask what is the value of cum sum, now I get 20, because what happened here is 2 plus 5 is 7, plus 6 is 13, plus 7 is 20. So in that way, I can add all these numbers together. Makes sense? A different way is number of, let's define number of elements, and I'm going to put that in 0, okay? This is another example of a cumulative variable. So instead, in addition to the previous ones, I'm going to say number of elements. It's going to be number of elements plus 1. So every time I loop over one of the elements, I add 1 to number of elements. So in this case, number of elements now is going to be 4 because I counted 4 times. Makes sense? Good. But again, play in the same way I was doing here, just playing with examples, define some vectors that are not too long, not too big, so that you can have an idea what is going on, play with the values, put some cat statements there to see what is going on within the full for loop, and then play a little bit with these cumulative variables that we define. Minxin has a question. Do we have to loop using the counter method? No, you can loop however you want. Actually, Minxin, this is a very good point I think you're raising. You could loop directly over the elements of x. That's another way to do it. And in this case, I will do just cat I in this way, and I just getting directly the elements. I'm not sure if you were referring to that in particular, but that would be a good idea in this case. I think I put the seek along example there just to don't make it too direct. But if you were just summing the values, why not, I would say. Is that kind of what you had in mind? You can do in length as well. Now, bear in mind, yeah, I see where you're going. So length, good point. Length, yes, you could use length of x, but remember one thing, right? Length of x give you just one number. So look what is going to happen if I do for I in length of x. It's a good idea. I just don't want to discourage you of doing this, but I want you to notice this as well. If I do this, I only loop once, because length of x is just one number. But I see what you mean. What you want, probably, correct me if I'm mistaken, please. What you want is one column length of x, because now you are looping from 1 up to how many elements are in x. And yes, you can choose then x of y. So seek along x is very similar. It's almost the same as doing 1 to length of x. Okay. But whatever method you want to implement, as far as it is correct and makes sense, you are welcome to do so. All right. Good question, guys. So this is the third part, the third function, sorry. In the first part is to implement, and as I say, I picked the positive mean, but you can do the harmonic mean if you wish. One of these two functions has to be implemented using a for loop and a condition, all right, instead of slicing and vectorization. Now, the second part and final part of the assignment is to create a script called testmeans.r. And this is what is going to be our main driver script, basically, because what it has to do is it has to source the functions definition files that we defined before. It has to create 5 vectors, okay? So 4 of these vectors come from the examples I'm giving you here, 1 to 10, minus 3 to 5, this particular vector and this other vector, and this additional vector. So 5 cases. And I want you to run these 5 cases in all the 3 functions, okay? And print the result in the script. So your script, your main driver script will basically source the function definitions, define 5 vectors. I will suggest to go back 1, 2, 3, and 4, and 5, and reuse these vectors to check the results of these functions and print them in the script, okay? So when I source your script, it should be printing the results in the screen. Okay. Any questions about the assignment? One important thing, which we will be paying special attention to comments in the code. So in particular, when you're doing the slicing and the vectorization operations, I want you to be explicit, saying, okay, I'm slicing this operation or doing this in this way because it represents this and that, okay? Document your functions. So you will have 3 functions. Each of them has to have proper documentation, indentation on the codes, and meaningful variable names, all right? You will have 2 files to submit, the functions files and the main driver script. And the due date is 2 weeks from now at midnight, March 29th, midnight, all right? Any questions? All right. Okay, guys. All right. If you guys don't have any further questions, then I will see you on Fridays. We still have the office hours. Remember, if you guys have any questions about the lectures or the assignment, also feel free to post something in the forum or just send me an email. Either way will work. Okay. And I will see you on office hours on Friday or on Monday next week. All right. Okay. Have a good one, everyone.